Assalamualaikum warahmatullahi wabarakatuh, and welcome to the undergraduate project presentation. My name is Amirul Ammar bin Mazlan, and I am a student of Bachelor of Mechanical Engineering. Today, I would like to talk with you about my project, which is the study on acoustic chamber performance. Throughout this project, I was supervised by Dr. Zair Asrar bin Ahmad, and I am very thankful for his advice, guidance, and suggestion during the entire project. Without further ado, here are the outline for this entire presentation. So, what is an acoustic chamber? Acoustic chamber or anechoic chamber is an important tool for the free field measurement. It is a chamber without any sound reflection coming from the wall, ceiling, or floor. The anechoic chamber walls are layered with sound absorbers in order for it to be echo-free field, which means that it can completely absorb the reflections of sound. The chamber can be used for measurement of various acoustic parameters with high precision. There are two types of chamber. First is the fully anechoic chamber, and the second one is the semi-anechoic chamber. For this project, the acoustic chamber is considered as fully anechoic chamber. As you know that there is an unusable acoustic chamber at the lab, so before we can fully utilize it, it is important to repair and measure its performance first. The chamber also needed to follow a correct standard to qualify it as an anechoic chamber. Why is it unusable? It is unusable because first, it has damage to its lining. The second one is the door cannot be closed tightly. And the final one is its foam is in worse condition. We also do not know whether the acoustic chamber follows a proper standard or not. Well, here is my research objective. As you can see, I have 4 different objectives to be met for this project. And now, this is the scope that I have limited myself for this project. As you can see here, okay, moving on to the literature review. Here is the measurement of performance, which involve sound pressure level with respect to distance, and the deviation at different microphone traverse. Then, this slide shows that it is the requirement to measure the performance in terms of the sound generated, the measurement point and distance, the sound source criteria, and the microphone must meet its requirement. So, most of the research that I have studied are using this type of standard. So, for this project, I choose the standard of ISO 3745. So, before we move on to the testing, we need to know how to get the estimated inverse square law. Here are the equations used in order to obtain the estimated inverse square law. Okay, this is the continuation for the equation before. Here you can read it. Okay, moving on to the next step is the methodology. On the right side is the procedure for the performance measurement. The first step is on the normal traverse. I place the microphone traverse on the first measurement point, and then I will start to generate the ping noise by the sound source, and I will record the sound pressure level of ping noise from around 250 Hz until 16,000 Hz, and I will move on to the next measurement point, and I will repeat the step until the end of the measurement point, and finally I will change it to another traverse, which is the dihedral and the trihedral corner. Here are the examples for the dihedral as well as the trihedral corner. This slide, this is the figure which shows the top view of the chamber, showing the different microphone traverse. Okay, this is the side view of the chamber. As you can see, the speaker and the microphone are shown here at trihedral and normal path. A more suitable setup to test the performance of the chamber is by putting the sound source at the end of the chamber. As you can see from this figure, the speaker are at the end of the chamber and the microphone are away from the sound source around 50 centimeters. Foam parameters that I've used throughout the testing: the initial foam,
the without foam, and the acoustic foam with thickness of 2 cm, and finally the 5 cm thickness.
Each foam parameter, the testing will be done based on this flowchart and the next flowchart, namely the testing from the center of the chamber and the testing of end-to-end chamber. The difference between this flowchart and the other flowchart is on the frequency as well as the traverse, microphone traverse. This flowchart only has one traverse, and this frequency has only two, which is the low and high frequency. Okay, the most important part in this presentation is the result. In this session, I will explain about the improvement made to the chamber. And the second one, I will show you the result of the performance between 4 different parameters. And finally, I will show you the performance result of end-to-end testing. The first improvement that I've made to the chamber is on the insulation. You can see that this is the before and after installing the new insulation. Improvement on the chamber is on the door. The first one is the door before modification, and the second one is the door after modification. You can see from the new door handles and the after modification. The old foam, which is the initial foam condition, has been changed to new foam, which is the 5 cm thickness.
These are the performance results between parameters at 250 Hz. As you can see here, on the normal traverse, all 4 parameters free field decays are not within the tolerance limit, which is the plus minus 1.5 decibels. The same results are shown for the other 2 traverse, which are the dihedral and the trihedral path. These results are due to the acoustic foam inability to absorb the noise frequency of 250 Hz. At this frequency, the power of the noise is higher, which causes the foams to be unable to absorb the noise efficiently, and some of the noise will reflect back from the chamber's wall. These are the performance results at 500 Hz. On the normal traverse graph, the data for all foam parameters are shown that the free field decays are not within the tolerance limit. The worst performance can be shown at the without foam condition. In all 3 traverses, as there are deviations that exceed the limit set by the standard. The power of 500 Hz may be lesser compared to 250 Hz, but the power is still higher for the acoustic foam to fully absorb it, hence causing the increase in the sound pressure level near the end of the measurement point. As the microphone moves nearer to the acoustic foam, the high energy can be detected by the microphone and causing it to increase the reading of the sound pressure level at the end of the traverse. So in short, the energy or power for the 500 Hz of the pink noise generated are still higher, and the foam parameters are unable to fully absorb. Next are the performance results at the lower middle frequency, which is the 1000 Hz. As you can see that all the foam parameters are not within the limits of the standard set by the ISO. This is also due to the high energy which caused the foam inability to absorb it efficiently. Okay, next is the performance result at 2000 Hz. Here you can see that there are some improvement that can be seen at the acoustic foam thickness 5 cm. On the normal traverse, it is within the limit set by the standard, as well as the dihedral traverse. Even though the trihedral traverse are not within, but it still almost follows the standard, which is the plus minus 1.0 decibel. Starting from 4000 Hz until 16,000 Hz, the normal traverse of 5 cm thickness foam parameters has shown a lot of improvement, in which the deviations are within the tolerance limit of the standard. When the deviation of noise are within the limit of plus minus 1.0 and plus minus 1.5 decibel, it can be considered to be qualified as an anechoic chamber. Even though there are some points in the trihedral traverse that are outside the limit, it is still acceptable as the cause are due to the reflections by the walls. Comparing the different foam parameters, the 5 cm thickness foam has shown considerable performance, and this can be seen in the figure shown here. The worst performance is the no acoustic foam parameter, or the without foam, as the data shows that the sound pressure level are higher in the latter point as the reflection of sound from the walls contributed greatly to the data. These are the performance result of 8000 Hz. As I've mentioned before, the performance of the acoustic foam at thickness 5 cm is very much inside the tolerance limit. So in short, for this testing, the acoustic chamber has shown that at low frequencies, the performance are not up to standard in all three different directions for all foam parameters. This can also be seen at the lower middle range frequency, which are the 1000 Hz and 2000 Hz. All the three paths have shown the deviation are not within the limits. These are due to the sound being reflected at the end of the path, affecting the estimated inverse square law, which caused a large deviation. While starting at 4000 Hz until 16,000 Hz, the performance of the chamber saw an increase when using the 5 cm acoustic foam. These are largely due to the fact that the foam are able to absorb the noise more efficiently. Okay, here are the performance results of end-to-end testing. The results shown for the low frequency of 200 Hz in all four foam parameters shown that the performance do not meet the inverse square law performance. It can be implied that the chamber or the foam used cannot absorb sound with low frequency. However, for the high frequency testing at 16,000 Hz, the chamber performance has shown that most of the foam parameters follow the inverse square law performance. Even though there are points nearer the sound source, they are outside the limits, which can be due to the near field region of the sound source. So, in short, both of the testing has shown that the chamber can perform well for the high frequency testing due to foam's ability to absorb sound or noise externally. However, the chamber will perform badly with the testing of the low frequency, which can be observed from the graph I've shown before. Therefore, for future testing, it is important to know or to determine the frequency of the equipment first before testing inside the chamber can be performed. So, the conclusion is, first, I would like to say that the objective for the improvement on the insulation performance using foam has successfully achieved. When the foam parameters are damaged or has defects, the performance of the chamber will be greatly affected. This can be seen from the initial results of the chamber performance. The different foam parameters have shown different results for the 1/3 octave band frequencies. Among the different foam parameters, the worst performance can be observed by the without acoustic foam condition, while the best performance is shown by the 5 cm acoustic foam parameter. For this project, the objective of studying the relationship between foam parameters and the performance of the chamber has been completed successfully. From the experiment that has been done, the foam parameters contributed greatly to the performance of the chamber. Therefore, the chamber can perform very well when using the acoustic foam with thickness of 5 cm instead of the acoustic foam with thickness of 2 cm. The difference between the two foam thickness are shown at the trihedral path, as the thicker the foam, the better the absorption of the noise near the walls of the chamber. Therefore, the sound pressure level taken at the end of the path can be reduced more effectively. There are different types of parameters that can be implemented to improve the measurement for the performance of the acoustic chamber. My recommendation are as follow. First is to use different type of acoustic foam. Second one is to install thicker acoustic foam. And next is to use different microphone mounting. And then use pure tone frequency instead of broadband pink noise. And the next one is to measure the reflectivity of the chamber, and the final one is to use higher frequency at above 16,000 Hz when taking the data. These are the reference. These are the continuation of the reference that I've used.
Okay, that's all from me. Thank you for watching and listening until the end of this presentation. Goodbye and have a nice day.